Thank you for staying until now. Um, so imagine that you're a data engineer. Building data pipeline is part of your company product. It is a data product that serves data insight to customers. The architecture involves running Apache Spark, Data Lake, Airflow, and all sorts of tools. You're working with petabytes of data, and every record matters. One day, your task is replacing one of the logic components of a legacy data pipeline. You don't know the code base that well. There is a testing system in place, but it doesn't really cover the data value and velocity. It's minimum and should guide you around the existing system. So you develop the code change, testing, staging, push to production, and hope for the best. Because YOLO. So when a customer calls you a few days later, asking to clarify the dashboard result, you're not surprised. You knew something like this going to happen. Does it sound familiar? So this is what we're going to talk about today. We're going to talk about how can we operate in this world when we have those complex data systems we cannot always rely on. There is no best solution, and the only reliable place to test petabytes of data is in production. I recently listened to a great session by Alden Caro, and she said we cannot expect Spark to just work. There are hidden behaviors that can result in data inconsistency. And those hidden behaviors arise from the challenge of complex computation of data. For example, you can see here a new feature Spark 3.0 just added called the adaptive query execution, with the goal of speeding up Spark SQL at runtime. So what it does, it dynamically makes a decision on top of every operation Spark thinks it's part of the DAG. It dynamically calls shopper partition, dynamically switch, optimize your joins, all in one time on the fly, without knowing this in advance, all when we have zero control over what is happening in our data pipeline. Knowing that, what can possibly go on with data flows that has all those moving parts? So basically everything. If you want to deploy new logic into the data pipeline, if we want to introduce a new data source, it might be that we created a new schema change or a new schema evolution that we don't know how to support. Sometimes we want the same Spark job twice because the previous one failed, but there's still some data there in the data lake. We don't go back and delete it. Sometimes we want to change tables relationship keys that can cause connection issues in between different components we develop. And maybe we want to fix something in production and accidentally deleted yesterday events partitions. And all that may lead to data duplications and other problems, inconsistency that we see in our data. And you must be thinking, no, we can test it, right? We have unit testing, integration testing, system testing, end-to-end testing. We have all sorts of testing that we can do as software developer and data engineer. But the reality is, and this is a great quote by Matt Weil, is many times our tests fail and we still commit the code to production. There is a lot of problems with testing systems that cannot cover everything. But sometimes more than enough, we don't trust it because of flaky tests and everything that happens in production. So we're going to reach a point we're going to say, I'm going to disagree and commit. I will disagree with my failing tests and commit my code to production anyway, because I can. So hey everyone, my name is Eden. I'm a software engineer at Trivers. We're focusing on developing industry best practices for working with data systems. Our team was exposed to many of the challenges and frustrations such the one I just described. We collected and tried to think together how can we improve the systems in order to build resilient into the system. I'm going to suggest you some best practices that worked as the chaos engineering world that comes from the SRE world, that comes from the DevOps world into the data engineering world. And in one sentence, chaos engineering is the discipline of experiencing software system in production in order to build confidence in the system capability to withstand the tolerance and unexpected condition. So that means for us that we're going to run testing on our production data. So how is that when we still layers data records in production without layers of protection? How is that when so many records are at stake? For example, our business, we never took the time to embed practices and started that will allow us to enable scalable data and distributed data pipeline. So this is what I want to talk about. How can we develop a large data lake with more confidence and build up, protect our production system from unexpected scenarios? We're going to see some best practices that worked at the SRE world and the DevOps world and see how we can find an equal solution in the data engineering world, in the distributed data system we're working with today. So chaos engineering practice 4 different principles. The first one is the steady state. We need to be able to define what should be the status of your environment before, after, and potentially during a chaos experimentation execution. What we want to see. We need to acknowledge there's going to be a variety in this world. Not everything is going to be perfect. The test won't cover everything. We need to be able to run experimentation in production, and we need to be able to automate this experiment as well. We're going to see how can we apply them to the world of data. So chaos testing different from regular testing, that instead of just looking for input A that will lead to output Y, we would want to check for the unknowns, for the unexpected scenarios that our system would want to prevent for. So the first principle speaks about the steady states. So every solution that we develop, every data pipeline that we develop, we always develop it with base of SAT in mind. We're aiming for steady states. And steady states means we want to have a specific system throughput. From a data engine, from a SRE point of view, and the chaos engineering would then look for system throughput. We would want to control and predict error rate. We would want to develop the system with a defined latency, and many more. From a data engineering point of view, we have data products requirements. This is always a big question. What are data products? What are data products requirements? So data products, basically, we solve everything to do with our data pipelines. We build the data pipelines, we build the data flows, and now we're producing data products that a company will sell to customers or using internally by data users. So it could be analytic, machine learning, decision making on top of my data, and many more. Into our data products. So this is a scene from Aladdin when he meets Jasmine and asks her, do you trust me? And the same question applies to our data products. Can we trust it? If this is what we're selling, if this is the main agent for our business, if this is what we're basing our business decision off, can we trust it? And data quality is a big issue for all of us building data system. We need to think about accuracy. We need to think about customer looking for data, customer looking for insight. Can we introduce duplication? Can we not introduce duplication to my system? Does the end user trust the data? What is the contract? What is the SLA? So we need to be able to define a specific requirement in order to serve our customers. And if we fail on delivering this specific accuracy and data quality, this often means customer churn. And if the customer is internal, it might mean that the rest of the company will start trusting our department. And it's a big issue, right? We don't want external churn because it's bad for the business, and we don't want internal churn because it's bad for us as engineers. So you probably wonder how easy it is to create data duplication into my system. I mean, why would I want to introduce data duplication? It's usually avoidable. Well, apparently it's not. Here's a good example. In just 3 lines of code, I can introduce data duplication. So we were reading a data frame from Parquet API, some band transaction. You all know that system will definitely want to make sure there's no data duplication, unless it's a plus for all of us, and this is great. But what about payments that goes out directly from our account? So definitely something we don't want to have there. So we're reading the data frame using S3 with a specific timestamp from S3, and we're performing some update on it, some transactions, some enriched method of the data, and then we write it back to the same folder. However, when we write it back, we use append. Append means we're actually inserting back all the transaction and actually duplicating our data. So it's great that we did it transaction, but instead of overriding, we made a tiny mistake and wrote append, and now we duplicated all the data. So this is something that happens frequently to data engineers. Not because of lack of knowledge, just because how the API is built and how easy it is to create, to have human errors and make mistakes. Now that we acknowledge that there is a steady state, let's speak about the variety of real-world events, such as human errors and mistakes that we do. From a data engineering point of view, we would look for hardware failures, like servers who are dying or spike in traffic. From a data engineering point of view, we would look at schema changes. Something happened, a new file, a new data source was added. Someone accidentally corrupted the data. We also need to acknowledge that there is data variance. We can support everything and all the scenarios in our testing system. And maybe you want to fix something in production and accidentally deleted yesterday events partitions. So unfortunately, real-world events is happening. So we really love our weekend. We really love go to the beach, but when data alerts come in, we gotta go and pick up the phone and start solving them. And many times it takes us away from this wonderful weekend. So what can we do? What chaos engineering suggests us to do? Chaos engineering suggests us to run experiment in production. We want to be able to uh, check the production machine and network. And from a data engineering point of view, you'd want to check the production data. And the goal here is to guarantee the authenticity of the way the system is exercised, and also develop a control environment when we know we won't harm our customer in production data. So that means for all of us that we're going to run experiment on our production data. And if it sounds scary, you're right, because no one wants to lose petabytes of data. So what we did until today, if we acknowledge that best practice, we start copying the data. Yeah. Yeah, so not everyone has a staging environment, and this is exactly what I'm going to suggest to you right now. Okay. Yeah. So what we did until today, if we acknowledge the best practices, we just started copying the data. We created different buckets or different folders, depending on which file system we're using. So if you're thinking about it, we're leveraging something that exists in software development for many years. We're leveraging the branching capabilities. For example, if I have here my main bucket in production, the data repo, I can just copy it, give it a whole different path. It's really easy with data source and S3. I can use the AWS CLI and create a chaos experimentation copy of my data with production-like data. So if you think about it, it's like doing what we're doing with Git. We're copying all of the data, and now we can work on it directly. And now that we know that we be able to run experimentation in production, we want to be able to experiment this way, to automate this experiment as well. We want to be able to run it consistently in order to discover these weaknesses. From a data engineering point of view, we would want to develop something completely new called the data lifecycle management. So we want to enable these different stages in production in order to test and qualify our data. So data stages has 3 different stages which we can leverage. The first time is development. Now that we copy all of the data, we can work on top of it in an isolated environment. We can use it to experiment, debug, and collaborate on it without harming the data in production. The second thing is the deployment. We want to be able to control the different version of the data that we have. For example, I have 2 main data streams. So we want to be able to control them and make sure we pass some of the best quality and performing quality check on top of it. And the last thing is production. After I copy the data, I want to be able to troubleshoot and go back, roll back in case I inserted bad error to production. So all of this requires a lot of manual work for us, and you probably wonder how can we automate this data state propagation inside our production. Today, many of us wrote some bash script or did it manually with the Azure CLI or the AWS CLI, but what is a better way of doing it? So what I'm suggesting to you today also comes from the DevOps world. This is the continuous integration, continuous deployment, only for data. Like we're doing with Git, copy our data, but only in a very managed way. For example, here I have my main bucket in production. I can just copy the data to a new feature bench, add my new data to it, and before merging it back to production, I can run quality checks using the pre-merge hook and validate our data. So all of that requires a lot of manual work that can cause human errors. So this is why we created LakeFS. LakeFS is an open source tool that turns your object store into a Git-like repository. It lies between of the object store and its using app and provides you the same versioning capabilities we believe it misses. So you work on top of it like you work on top of S3 and your object store. You can list the objects, write them, read them from there, and on top of it, it gives you the versioning capabilities, like revert data, merge, and create an isolated environment. So let's see how can we apply those principles into our daily work with LakeFS. So if we need to quickly recover from an error, we inserted the data error or data corruption to production. We didn't copy the data in the past. We don't have a copy of it. We can simply revert a commit in our main branch to a specific point of time where data was still valid. If you want to experiment on production-like data, you can just check out of your main branch and create an isolated environment where you can perform all the testing and all the chaos testing in the world without harming the data in production. And the benefit using LakeFS here, you don't actually do the copy. We all know S3 is relatively cost efficient, but it's not 100% free. So doing it with LakeFS gives you the same copy, but without actually copying the data. Troubleshooting. We want to go back to a specific version of the file, a specific version of the dataset, and troubleshoot it, debug it, so I can just read my file from S3 with a specific commit ID that represents the time of the commit. Atomic update. I checked out to my main branch, to my development branch. I did my testing there, I did my development there. I want to merge it back to production. I can just merge it. And the merging will be atomically. So if I have multiple data sources running simultaneously, like Kafka, once I'm performing the merge, I'm merging them all in once and created this unified view that helps me to debug and track my data. And last is probably one of the most complicated cases to do for us manually. We want to be able to reprocess. We know something had happened, some errors occur. We want to go back to specific version and change its logic, enable this update, and then develop 2 different data pipelines with 2 branches. And once we are satisfied with the result, merge it back on top of my production data, and I can work on top of it. Yes, so with Git, when you have like your branch, it saves you kind of list of all the specific commit, and where like we using like all your data is saved in the object store in a one folder, right? Like you have a data lake with a bunch of data waiting there, right? And there are like multiple data sources that waiting to the lake, right? And everything is waiting to the data lake. You're working with S3, with Azure Blob. You have a point where all of your data is saved, right? Yeah. Yeah. I mean, okay, so LakeFS does the same thing as Git for code, like just like the Git for data, okay? So how it does it? No, it's LakeFS is Git for data, if I didn't mention it. So LakeFS is, yeah, it's Git for data. So like I said, you have your bucket in your object so that all your data is saved there. And instead of writing your data to it, you're writing to LakeFS. And yeah. Because when you read it, you don't read it from like the database. You read it from LakeFS. And LakeFS will give you the specific version. You will add to like, if you want to read file A, you will say, I want to read file A with the commit ABC. And LakeFS will give you the file A in the version of the ABC commit. Yeah. Yeah. No, when you read it from a specific commit. You're adding the branching to the data. I mean, you not want a collection, you're gonna main collection. So yeah, it's added, but when you read it from a specific version. You have different version of the data. Right. Yeah. No, but when your customer reading the data, they're reading it from a specific version of it. So LakeFS will return them the reverted data. If So you would have like, I don't know how it's work, we can like talk about it later, but maybe you can just like, I don't know, you ask to release again, I don't know how your customer getting the data. So, but you would have to do something for it to be manual today. I'll explain more later, okay? So I'm suggesting there are some engineers here today, and you probably wonder how LakeFS works. Because like we said, it's a zero copy mechanism. So LakeFS does not save your data. All your data saved in the object storage. And LakeFS only uses the metadata to maintain the versioning info. So for example, you can see I have a commit that points to a files in the object store. After some time, another commit was created, and only one file was added. So creating a new branch, for example, is practically zero cost because the new commit only points to the parent commit. So we're not actually duplicating our data. So all our operations are copy on write, which provide great performance on big data lake. So let's see how can we put those together in our chaos experimentation, and let's see how a typical environment would look like. So we will have our main bucket in production, which is extremely valuable to our customer and we want to protect. So, and we would have another branch that will introduce new changes for multiple data sources, for example, Kafka Producer or Airflow. And once in a while, depending on my use case, I want to merge it back to production. And before I merge it back, I want to run quality checks, pre-merge hook, the CI/CD for data. I will want to check there is no broken schema. I will want to check I didn't delete a specific file under user partition in production. So I can do that with KFS. So, and if I want to experiment, to do a chaos experimentation on production-like data, I can just check out of my production branch, work in isolation, and once I want to merge it back, I can just merge it. Now I'm going to do a really quick demo. Okay, so this is LakeFS. You can see I have my repo. I have my list of repo. I created a new, I already created a repo. The repo is pointing to a bucket in S3, bucket or a prefix or whatever I want to manage. I added a book table. I can see I wrote it with Spark. If I want, I can just import a new objects from other places. I have here I can see my uncommitted changes. We will do it in a few minutes. My commit log that represented all my commits. And in the actions is where I will introduce my CI/CD, where I can run my quality checks before merging branches. Here I have a Databricks notebook, and I will just show you just a few operations. So LakeFS, like Git, has the UI, has the CLI, and also have a Python client. So if I want to list branches, I can see I have my main branch. And now I wanted to introduce a new branch, a chaos experimentation branch where I can introduce my changes and perform testing without harming the data. So I'm creating the branch, and now I can see here. I have my chaos experimentation branch, which holds the exactly same data, again with no copy. And now when I'm working on top of my developing my data pipeline, I would have my main repo that will represent the main, and I have the chaos experimentation branch. So whatever I want to, I can just like choose the right path for me. And even if I make a mistake and write my data to the repo path, I can still revert a commit. So I can just like upload an object. I will add an object to the chaos experimentation. Okay, it's uncommitted. So now I can, before I will commit, I will just maybe delete some objects. Okay. And now I can commit it. I can see it in my commit log. And now I can compare my main branch into my chaos experimentation branch. Okay, so I can see I deleted some files, I added some files, so now before merging it back, I can see what changes I introduced. And if I decided it's okay, I can just merge it back to my main branch. This is basically it. Um, so today we learned about how can we adopt the chaos engineering principles into the data engineering world. We learned what is the data lifecycle management and the importance of them. And you know what is Git for data, which is like FS. I also want to share that we have a really vibrant community. We are open source. We are trusted by more 1,000 companies. We have more than 4,000 active community members in our community. And if you have, we would really love to gain from your experience checking out LakeFS. And if you have any question, I'd love to answer. Thank you. No, it's work on all object store, like Azure Blob and GCP as well. Yeah. Right. Yeah, you can revert like you do in Git. Yeah. So if you have another like sources of data that you want to be able to control, so maybe you should like insert it to another branch and then merge it to production, whatever you want. And then you can control it without all of the data in production. You will be able to control the changes. Yeah. Yeah, exactly. It's like what we provide the S3 compatible API, so all your operation you're doing on top of your object store, it's the same. You're just pointing into LakeFS. To LakeFS that points to the folder that holds the versions. Yeah. No, it is for ongoing because if you want to manage it, you have to write all your data to it because if you will write it to a different place, you won't know how to manage it. You decide to commit. You decide whatever you want to commit. No, but you have API. You can you can write a script that will do it for you. Like every 10 minutes after a new file was added, a new process, you can just commit it. Yeah, so you don't have to do it manually using. I just show you the UI because it's easy, but there are like clients for it, like the Python client. Okay, it's okay. Any more questions? So, so it's a different service, but you have to run like a FS server somehow. You have to decide where you want to manage it. Like it could be Kubernetes, whatever where you want to manage it. Yeah. Great. Thank you.